Okay, we only have 2 areas that are calculus-based to be worried about for the exam. Area number 1 is the Maxwell-Boltzmann distribution. And so with that, you need to be able to, there we go. You need to be able to calculate the sum of the probabilities. By definition, what should the sum of the probabilities be? If I have, this here is, by definition, what should the sum of the probabilities be? 1. Right, that's probability of a given particle having any speed is 1. And then this Maxwell-Boltzmann equation, of course the equation is given on the equation sheet. I sent you the email, you requested when I posted it.
Thank you.
I have made one change since then, and that was taking out the redundant equations for temperature changes and putting in the specific heat of water.
Are we going to have the percent humidity equation on there, or are we not going to need it?
As I said, yes, so you're not going to use it. Okay, so how do you calculate that sum of the probabilities? Because it would not be sufficient if I say calculate for you to say, well, by definition, it has to be 1. So how would you calculate it? Ready?
Long chapel.
I've got a probability distribution. If I want to find the total of all the probabilities, how do you do it? You integrate. You integrate over the entire range of possible speeds. At this point, it's not the true range, but what's the theoretical range at this point in your life? 0 to infinity. Later on, we will see, yes, the actual maximum speed is 299792458 meters per second. But for now, we just pretend it can go up to infinity. How do we do that integral? I give you a sheet with the equations, right? We had 4 different equations, I think, on that sheet. Who's this? James. Did you guys just come from chapel as well?
Yeah.
I'm actually going to count you all on time because I'm that kind of generous today. Can't blame a person for going to chapel, right?
Yeah, she was praying so nobody could leave, and she just kept going. Guess.
I'm not going to talk about long prayers. Ellen White did speak against long public prayers. Just, of course, I think her definition of long and mine are 2 different things as well. It has to do with attention spans, mine. Okay, so we would have that list of integrals. So I would just give that to you separately along with the equation sheet for problems like these. How would you find the most likely speed then? Okay, to find the most likely speed, you just want to find where the maximum is. So you take the first derivative, set it equal to 0, and find the speed that makes the first derivative equal to 0. That's the easiest possible question I could ask, probably. Then to find the average speed next. So the most likely speed was take the derivative, set it to 0. The average speed, I'm not sure if I said most probable or average the first time, but I know the answer was for the most probable. How do we find the average speed? We have a weighting factor, the probability. And so if we were doing the average score on the test, we would take our weighting factor for each score, multiplied by that score, add them all up. And assuming that our weighting factors add up to 1, just like we have here, that'd be the end of it. The weighting factors didn't add up to 1, we divide by the total of the weighting factors. So we do exactly the same thing here. Our weighting factor is this probability. So to find the average speed, which we write like this, we integrate the speed multiplied by that probability function over all possible speeds. So that would give us the average speed. And if you know how to find the average speed, you probably know how to find the average squared speed, right? Because what's the difference between finding the average speed and the average squared speed? You put the square in there. And then finally, how do you find the RMS speed? What's the definition of RMS? What does RMS stand for? Root means square. So you have to take, square your values, that's v squared. Find the mean, that's what I just said. You take that integral, but it's v squared f of v. And then you have to do the square root of it.
So it's just the square root of the average speed?
So, no. It's the square root of the average of the speed squared. So that means it's going to be the square root of the integral So that's how you calculate the RMS speed. Now, I hope no one ever writes it the way I wrote it in the last form there. Right? That's annoying to me. You would say, okay, let's find the v squared average. Now let's take the square root, rather than putting the integral under the square root sign. So those are the things that we have with the Maxwell-Boltzmann distribution. Could I ask other things? Yes, I could. I could ask you, what is the v to the fourth average? If I asked you what the v to the fourth average is, which I would probably write as this, to make sure there's no confusion about where the to the fourth power goes. How would you calculate that?
The integral of v to the fourth f of v dv.
Yes. Right, so once you know the basics, it's easy to have these other options. So, you can ask a plethora of questions, and I could ask you a simple question, what is the 1 over v squared average? Why is that simple? Because then this would cancel out. That would make life easier. So there's our method for that. Any questions about the Maxwell-Boltzmann distribution?
Can we do a problem?
Can we do a problem? Sure. Which one do you want to do? Name one, we'll do it.
Just the average speed.
Okay. So the average speed like I remember this, m over 2 pi kt. So there was it 3 halves. So I have this thing. And I'm not going to finish it out because I would have to have my little integral table because I don't know these offhand either. So that's as far as I can go without having my little table to then just use the worked out integrals for me. So at this point, I'd look to my table and say that's equal to something I3. Make sure you have your, A in that table was, I think, the coefficient of V squared, wasn't it? I don't have the table in front of me, so I can't tell you what it is. But I think that you would have A equals,
And what happened to the 4 pi?
I forgot it. I tried to take out all the constant and forgot that part of the constant. And so you would have to take into account what A is and then just use that table. So that would be I3 because the exponent of the V it was 3. And I3 is some function times I1, and I1 we had a value for.
So you're providing A and B?
Well, remember that sheet of paper that I handed out?
I think I have-
Yeah, so that's what I would be providing for you to use in solving.
So we'll have that sheet, or we can.
Yeah, if I give you a problem with this, I'll give you that sheet as well.
So to be clear, this equation can change the F with the equation, or is this the Maxwell-Boltzmann?
That's the Maxwell-Boltzmann distribution. There are a couple different variations of it for different situations, but this is the general situation of just an open chamber. And so that's the only equation we're going to have for it.
Is this the right sheet? That must be-
Yes, that's the right sheet. I thought it had A in the exponent. Does it have?
It uses A, but it doesn't define what it is.
Oh, yeah. So, right, you just match this against this and have A is the 1/2 and over KT. Just by matching these two things together. You still have a question there, Caitlin, or?
Yeah, I might just ask you.
Okay. Ask me tomorrow? Okay, I know that wasn't as funny as it sounded to me. Okay, the other type of problem we could have would be a thermodynamics problem. Now, some of you might be chemistry majors and you'll be taking physical chemistry thermodynamics down the way, and you'll be looking at these things much more in detail than we do in a general physics class. If you're a physics major, we have a physics version as well of thermodynamics. As far as you're concerned in general physics, it's pretty simplistic. You only have a couple equations. Right? If you learn the Maxwell's relations in your thermodynamics class, you're like, this stuff is so basic. So those are our equations we're going to work with, and you need to be able to use those to do things like calculate the work and or change in entropy under various conditions. So the conditions could be adiabatic, isochoric, isobaric, isothermal, or it could be a specified situation such as the heat as a function of temperature is this, or the pressure as a function of volume is this. So let's just, we've done all of these except for the random ones, but let's just look at one, like let's say, something that you've done in the homework recently. What is the change in entropy for an isochoric transition? Well, what does the word isochoric mean? Okay, so the volume is constant. So that's the first thing you'd have to do here is to identify V is constant. And if V is constant, if it's isochoric, we're talking about a gas. And I should have said for an ideal gas. But even if it's not ideal, we could still say that this is the relationship between heat and temperature change. Well, that's the non-calculus version. What's the calculus version of that equation?
CP natural level.
Just of this equation. You're going ahead.
TVCT is
We're going to put a DQ. If you want to be technical, you put something like a slash through that D because it's not really proper, is equal to NCV dt. The dt is proper. It's the dq that's not. And so then we take that in truthfully. You should have slashes in all of those. So now we can take our relationship that says ds is equal to dq over t. So that's going to be ncv dt over t. And now we can do what Gabriel was saying. He quoted us the answer, but of course, on the test, I'm looking for you to show that you understand how to get there, not that you for instance, can look on the equation sheet and say, well, it says right here that. I laugh. It's clear that some students, none of you guys, don't realize that the goal is not to just be able to identify the formula on the equation sheet and move on. It's a problem. Okay, so now that we have this, how do I find the change in entropy? Because they're independent, I have temperature is the only variable on the right-hand side, entropy is the only variable on the left-hand side. Because they're independent, I can integrate them, and as long as my limits correspond, that is my initial and initial correspond, my final and final correspond, it's still going to work, be correct. So I would have, right, the left side is really easy to integrate. You're going from initial entropy to final entropy, so S final minus S initial equals, and what do you get for the right-hand integral?
NCV natural log of TF over TI.
I believe you said TF twice, but I'm pretty sure you meant it that way.
I said TF over TI.
Okay. Yeah, that's correct.
Yeah, it may come out.
So there we have our equation for the change in entropy. So you would be asked to do something like this. Another option. So now you could have a question that's non-calculus question that has you just use the formula. The calculus-based question would say, show us how you get the formula. Right? Because you're given the formula, that hence non-calculus people can use it. It's understanding where it comes from. So there's a simple example, which you should have used heavily in your last homework assignment, right? The one that was due last night? Yeah. Like in problem 1, I think. Now, when you have NCV, that's for gases. When you have liquids or solids, I started saying something, I'm getting my wires crossed. So I'll stop saying it. Question, Aaron.
Will we be given CB and CP if we need to use them, or should we know how to explain that their 3 halves are and 5 halves are?
Caitlin has the equation sheet there with her.
Okay.
If you look, it says that that the number of degrees of freedom divided by 2 times R is the CB, and then you add the CB minus CP.
Oh, that's what the F means.
Yeah, it's defined. Oh, wait, where's it defined? It's defined somewhere here, I thought.
Second page near top.
Well, no. I guess it does not say that F is degrees of freedom, but that's what it is. And so, I mean, this is what you have. So notice that it tells you that for a monatomic, F is equal to 3. For a diatomic at room temperature, F is 5.
Are we going to have to do anything with diatomic at all?
The answer is yes. Okay. What else? I mean, anything else you want to see worked out here? Or? Carrie.
Calculating the work.
Calculating the work, sure. You want to give an example? Choose a situation you want to do, and I will do it. Work. Okay, that is the absolutely easiest one. I know, you were just randomly choosing. Okay, what does isobaric mean? P is constant. So, since dW is equal to P dV, if P is constant, that's trivial. I can put the P outside of my integral sign. And so that just becomes the work is equal to P delta V. And once again, you can see why there's really supposed to be that slash on the D, because it wasn't change in work, it's just work. Right? You don't have the work final and the work initial. Right? Those don't exist. You have the work that was done between the initial and final states. That's why you have the slash on the D. So now, who's going to...
What are the ranges in a limit?
This would just be initial to final. I don't care. Initial to final.
And we don't have to show that?
If in general, you can just use delta and be good with it. If it's a linear change like this, if it had like V dV, I would have to be a little more careful, because I'm not going to have delta V if it's integral of V dV. So it's only in this special case when I can be sloppy. So it's better not to be sloppy. It's better to put, volume initial, volume final. I can't put work initial and work final because those don't exist.
So work is just always work.
Yeah, and remember, that's why there is the slash on it, because it's the nomenclature is not being used properly.
So there could never be a delta Q either.
Correct. Okay, so let's do one that's more interesting. You randomly chose too simple. Somebody else want to?
Can we do one of those random situations of Q to your?
Okay, yes we can. No. I just think somebody say that. Obviously, I say yes to these kinds of requests. Okay, so let's make up a function for pressure. So let's say pressure is equal to some constant, I'll call it capital C, and then V raised to the, B. Okay, this is very generic. It'll work for any polynomial function for pressure as a function of volume. Given that, then I'm going to have, I don't know what happened there, but it happened again. Okay. Well, at least we've learned what to do when things go haywire. Maybe. Come on. Let me close it and start it again. Back in business. Okay, so there I made my substitution. Now I'm going to integrate both sides. So here I did have to be with the volume very specific, from volume initial to volume final. And on the work, I just put I and F because I can't get myself to write WI and WF since they're not sensical. Doing the integrals, then I'm going to have, for the left side, going to the sensical work for the transition is equal to C. Well, integral of V raised to the B power, what's that? Exactly. V to the B plus 1 over B plus 1 with my limits. And so that would be my equation. Right? That's a very generic, that'll work for any polynomial equation for pressure as a function of volume. What's the most common mistake you suppose people would make in this problem? It goes back to the question that Caitlin asked about the limits and my answer more specifically. She didn't indicate a problem. I indicated where a problem could come. Just want to make sure I'm not, people don't think I'm saying something wrong or something. What do you think the most common problem is? Yeah. The most common problem, and that's part of the reason why we had to do those, remember the 5 derivatives and 5 integrals, and the integrals were all with limits? Because oftentimes students come to this class and they're just not used to having the limits and putting it in. And so then they make that kind of mistake. The most common problem is for people to just take V final minus V initial parenthesis and raise the whole thing to the B plus 1, which is incredibly wrong. Oh, incredibly wrong. I mean, there's right and there's wrong. It's wrong. So any questions about that? No. All right, that is everything I had prepared. It's going to be something that falls within the range of what we've done this morning. It'll be on the test this afternoon. If I had just taught it for the first time this morning, that would not be fair, but we'll do it. Yes?
So both of the QT or PV situations, they'll be just functions, and all we really need to do then is just run them through the appropriate.
That's right. Yeah. Okay. If you understand, it's really not complicated. If you don't understand, it's hard, right? If you don't understand where you're going, you sit there and scratch your head. That's all I have prepared, folks. Erin.
I just have a question from one of the review tests that you put online.
Mm-hmm.
And it's about the change in the effective thermal coefficient. So it's question number 7 on one of the exams, and I don't have the exact question. I could pull it up. But it's basically saying that a piece of wood is put over a glass window pane, and it gives both of the thermal coefficients and the area and the thickness of both. And then it asks what the effective thermal coefficient is for them. And I can get some numbers.
Okay. Yeah. I can do it generically without the numbers, and I think we'll be good with the understanding. So what we have here is, get your color codes right. So we have K of wood and K of glass. And we have thicknesses, so we have the thickness of the glass and the thickness of the wood. And we want to find the effective thermal conductivity coefficient for the entire thing. So we start off by saying, how do I calculate the power that's flowing through conduction? So I have the power for conduction equation is power for conduction is equal to K times area over length multiplied by temperature 1 minus temperature 2. It's on the equation sheet, yeah. And so in this case, if I have heat that goes through the glass, what's going to happen to that heat? It's going to go through the wood as well. And so I have a condition that says the heat that flows through the wood is going to flow through the glass. So they're both going to have the same power. That is, once you reach equilibrium, you're going to have the rate of heat going through the wood is equal to the rate of heat going through the glass. That wouldn't be the case the instant you put the wood on, but once it reaches equilibrium. So we have our condition here is at equilibrium, P wood equals P glass. So I need to define temperature, so I'm going to call this temperature inside, temperature middle, and temperature outside. And then if I do my calculation here, I will have power for the wood is equal to K wood times area over the thickness of the wood times the, assuming it's hot inside and cold outside, and I'm calculating it going through, it'd just be the temperature in the middle minus the temperature outside. And similarly, the power through the glass is equal to K for the glass times area over thickness of the glass, temperature inside minus temperature in the middle.
Just clarify, area being the area of the pane.
Yes, the area is the cross-sectional area. So you have a window like that. It's the area that you're seeing through the window. So I set these equal to each other. I would have that relationship, right? So going through this, I can now find, well, first of all, let's be reasonable. Cancel what is obvious. Cancel the A's there. And I can find the intermediate temperature. That is I'm getting sloppy in my writing. Somebody should have corrected that sign error. When you add on both sides, it's going to be positive on the side you added it to, right? To add. I'm just writing the one addition because I made a mistake on it. Okay, now you probably are kind of frustrated because have we gotten anywhere close to our answer yet? No, we haven't. But we now have everything we need for our answer because let's go back and consider the equivalence. What's the equivalent K? Well, the equivalent K is going to be, say, let's combine these two pieces and say it's one object with equivalent K. And so we also are going to have for our equivalence, the power for our equivalent has to be equal to the power of the glass, has to be equal to the power of the wood. And that would be equal to the K equivalent over the sum of the two thicknesses. And then the temperature difference from one side to the other. So the temperature. And so now I'm going to take this equation here.
Do you have to put the area in as well?
Yes, I do. So I take this equation, I set it equal to either one of my first two. Now that I know what the temperature in the middle is, I can set it to either one and solve this. So K equivalent times area, thickness of glass plus thickness of wood, and let's just choose glass for random choice. So that's my equation I'm going to use. Whoops, that was an M for the last one, not a G. That's the equation I'm going to use. Once again, any reasonable person says, let's cancel out the area and solve this for KE. So I now have everything done except for I have to put that temperature intermediate, the temperature middle, into this equation. And you see it's getting longer and longer as I write, but we're only one step away, so I will just do it. I'm going to write this in a different color. Yep, that's it. And then there's some simplification you can do, but you basically put your numbers in and you find what the equivalence is. And I'm pretty sure that there's going to be some canceling. It seems like it shouldn't depend on the temperatures, but unless I made a mistake, that would be it. Did the problem give you temperatures? Didn't? Uh-oh. You should be able to, but it doesn't feel like it will. Oh, yeah. I unfortunately, with this program, I can't just copy and paste to another page. What was that code? Sorry. One's capital, one's lowercase. Okay, so we can get a common denominator by multiplying this by this term. And so if we do that, then I'm going to bring this here, and actually I can move it on this page. Well, I'm going to move that down to here, and then this here is going to be multiplied by that as well. And so temperature initial times KW over TW plus temperature initial times KG over TG minus, and I'm going to have a temperature initial KG over TG. So I'm going to have, I remember my trick. There will be plenty of room to write this. Actually, First, I'm going to shrink this down, and then I will do my work in shrinkage. Okay. I see I wrote the wrong T there. Were you actually referring to that and I didn't catch it, Cody? Okay, so now looking at the green, I see that this term here and this term here subtract out. And so I'm left with left with that. And now we can see the canceling of temperatures. So it is independent of temperature. And I am sure that you must be able to simplify this somewhat. KGK times KW over, yeah, I think I would just go ahead and put in numbers at this point instead of trying to simplify further. Because it's all in simple terms. And because I'm out of space, even though I shrunk, well, when you do that through I'm doubting anyone cares at this point. That's as simple as you can get it. Work for you?
You lost me.
Well, it was just simplification from, when I copied things, I took away those two, which of course is important. So this here, I couldn't really leave it there if they didn't give you the temperature. Well, actually, you had to put in the TM anyway. So I simply went from there, put in the TM, and then rearranged so that I could cancel. And the purple down here has the temperature removed. So it was just algebra to get rid of the temperatures. Because it really shouldn't matter what the temperature inside and outside is to what the conductivity is. It's a good question, right? That would be a level 3. It has them less difficult, more difficult, and most difficult. This test has no most difficults on it.
What would you classify this?
This would have been a most difficult just because of the multiple pieces you had to put together.
So not on the test.
This question is not on the test. That is correct. Okay, let's have a swell hour and a half.